All right, this lesson covers day 3, characteristics of polynomials, and we're talking about even and odd functions. It is important to realize the difference between even and odd functions and even-odd degree polynomials. Any function f of x is even if, algebraically, f of x, or f of negative x, is equal to f of x. That simply means if we take the original function f and replace all of the x's with negative x, the result would be the same as the original function f of x. Graphically, an even function is symmetric with respect to the y-axis. All right, and then for an odd function, any function f of x is odd if f of negative x is equal to the negative of f of x. In other words, if we take the original function f of x and replace all of the x's with negative x, and the result comes out to be the negative or the opposite of the original function, then it is odd. And graphically, an odd function is symmetric with respect to the origin. Now, what if it was true that f of negative x was not equal to f of x? Well, that would mean it's not even. What if it was also true that f of negative x was not equal to the negative of f of x? That means it is not odd. So it's possible that a function is neither even nor odd. So if it has neither of these two conditions, then we say it is neither even nor odd. Now let's take a look at these 3 graphs. Determine if the graphs below represent an even or odd function, or if it is neither. In graph A, you might notice that the points are a reflection through the origin. In other words, this point A reflected through the origin comes out at A prime. And point B reflected through this origin would come out at B prime. And C reflected through the origin comes out at C prime. So we clearly see that this graph has origin symmetry, which means it is odd. Let's go over to graph B. You might determine that this graph is symmetric with respect to the y-axis. So if this is the y-axis, you can see that there is a mirror image or mirror reflection across the y-axis. So because this has y-axis symmetry, this graph is even. For graph C, this graph is neither symmetric through the y-axis, and it's not symmetric through the origin either. So this graph is neither even nor odd. It is neither. All right, now in this lower section it says confirm your answers algebraically given the following equations for each graph. So what we're saying is that for part A, the equation for graph A is this equation here, the f of x equation, x to the 5th minus 5x to the 3rd plus 4x. So we're going to determine that this is odd algebraically. So let's do that. To determine whether a function is even, odd, or neither, you replace the x with negative x. So when you do that, we have f of negative x equals negative x to the 5th minus 5 times negative x to the 3rd plus 4 times negative x. Simplifying that, we get the negative of x to the 5th plus 5x to the 3rd. And that is because negative x to the 3rd is negative, multiplied by this negative 5 makes that a positive 5x to the 3rd. And then we have 4 times negative x is negative 4x. How does this compare to the original function? You'll notice that the coefficients are all opposite. This is negative x to the 5th. The original was positive x to the 5th. This is positive 5, the original has the negative 5, and this was negative 4x, and the original had positive 4x. So the result is the negative, or the opposite, of the original f of x function, and that's what makes this odd. Part B, we have f of x is x to the fourth minus 3x squared minus 1. Replace all of these x's with negative x. And this is the result. We have negative x to the fourth. That's going to simplify to positive x to the fourth. Negative x squared is the same thing as positive x squared times negative 3 gives us negative 3x squared. And then we bring down the minus 1. Well, how does this compare to the original function? It is exactly the same. So when f of negative x is the same as f of x, then it is even. And finally, in part C, replace all of the x's with negative x. And this is the result. And now if we take negative 4 or negative x to the fourth, we get just positive x to the fourth times the 4. Negative x to the third is negative, multiplied by the negative 3 makes that positive 3x to the third. And negative x squared is positive, times the negative 2 makes that negative 2x squared, and then we have the minus x. How does this compare to the original? Well, it is not the same, because we've got a positive 4 here. Those are the same, but the 3 is negative here, but positive there. So it's not the same, but it's not the opposite either. So in this case, we say that this is neither. It's neither even nor odd. All right, let's discuss x-intercepts and turning points. Each of the equations on the previous page can be re-expressed as a product of linear factors by factoring the equations. Factor the equation 2x to the third minus 5x squared minus 2x plus 5. We can factor by grouping because we have 4 terms here. And in grouping, we would group the first 2 together and group the last 2 together. Then we'd find the greatest common factor of each group. The greatest common factor in the first group is x squared, and you would be left with 2x minus 5 in parentheses. The greatest common factor in the second group is negative 1, and you'd be left with 2x minus 5 in parentheses. The 2x minus 5 is now the common factor in this polynomial. So if we factor out the 2x minus 5, we get 2x minus 5 times the quantity x squared minus 1. Now x squared minus 1 can be factored even further. That's the difference of squares. So x squared minus 1 becomes x plus 1 times x minus 1. And then you bring down the 2x minus 5. So we have these 3 factors. All right, part B, using the graph, list its x-intercepts. How are these intercepts related to the linear factors? Well, here is the graph. I've typed in the equation here, and we have 3 x-intercepts. The x-intercept on the far left is negative 1, 0. There's one in the middle at positive 1, 0, and the far right is 2.5, 0. So back on the page, again, those x-intercepts that we found on the graph were x equals negative 1, positive 1, and 2.5. Now, how are these x-intercepts related to the linear factors? They are the solutions to the linear factors above when you set them equal to 0. In other words, x minus 1 equals 0. When you solve that, you get x equals positive 1. And if you solve x plus 1 equals 0, you get x equals negative 1. And finally, if you solve 2x minus 5 equals 0, you would get positive 5 over 2, which is 2.5. And why might it be useful to know the linear factors of a polynomial function? Well, if you don't have a graph, you can still find the x-intercepts. You can find the x-intercepts by setting the factors equal to 0. no graph would be necessary to find the x-intercepts. Now, what about the degree? The degree of a polynomial tells you even more about it than the end behavior. Specifically, an nth degree polynomial can have up to n x-intercepts. Notice that an odd degree polynomial must have at least one x-intercept, and that is since the function approaches negative infinity at one end and positive infinity on the other. A continuous function that switches from negative to positive must intersect the x-axis somewhere in between. And in the last paragraph, in addition, an nth degree polynomial can have up to n minus 1 turning points. A turning point is a point at which the function changes from increasing to decreasing, or from decreasing to increasing as seen in the figure below. So this to me looks like it could be an x to the fourth or a fourth degree polynomial, and you'll notice that it has 1, 2, 3 turning points. So if this is a fourth degree polynomial and it has 1, 2, 3 turning points, that would be the maximum number of turning points. Hence, if the degree is 4, the maximum number of turning points would be 4 minus 1, or n minus 1, and that would give you 3 turning points. Right, in this last section, give the maximum number of zeros and turning points for each function, and then use your calculator to find the actual number of turning points and the value of the zeros for each. Okay, so for question number 1, we have x to the 5th plus x to the 4th minus 2x to the 3rd. And so with the degree being 5, we would have a maximum of 5 zeros, and the number of maximum turning points is 1 less than 5, which is 4. So we'd have a maximum of 5 zeros and a maximum of 4 turning points. If we look at the graph, we can see that we have 1, 2, 3 zeros and 1, 2 turning points. So that's the actual. So even though we have a maximum of 5 zeros, we only have actually 3 zeros. We could have a maximum of 4 turning points, but here we can see we only have 2 actual turning points. Question number 2, we can see that this is x to the 3rd, so this is a degree 3 polynomial. And because it is a degree 3 polynomial, it would have a maximum of 3 zeros and a maximum of 2 turning points. Here's the actual graph, and we can see that there are 1, 2, 3 actual zeros and 1, 2 turning points. So the actual number of zeros is 3, which matches the maximum number 3. And the actual number of turning points is 2, which matches the maximum number of turning points. And for question number 3, y equals x squared times x minus 1 times x plus 4. If x squared is multiplied by x and then times another x, we would end up with x to the 4th power. So we would say that the degree is 4, and the maximum number of zeros would be 4. And the maximum number of turning points would be 3. If we take a look at the graph, we see that we have 1, 2, 3 zeros and 1, 2, 3 turning points. So 3 zeros and 2 and 3 turning points. All right, and that is the end of this lesson.